Engineer at Datastax. I did a PhD at some point, so I know a bit about bioinformatics. I spent a lot of time with automation, and now I work for the Datastax on the analytics team, and one of my focuses is on the Datastax open source software, Spark Cassandra connector. And open source software is awesome, and the Datastax Spark Cassandra connector is as well. It will let you interact with your Cassandra data from Spark with a minimal amount of fuss. It gives you the ability to do bulk writing to Cassandra, distributed access to your Cassandra tables, optimize direct joins with your data, pushdowns on your secondary indexes and your clustering keys, and all kinds of other great things. Before I get into any of the details of how that works, I just want to make sure everyone knows that you can get it right now at sparkpackages.com. It's pretty much the easiest way to get access to it. Our GitHub is right below there if you're interested in looking at the source code and getting the very latest release. And below that, our friend at Target Holding Friends has actually made a complete Python wrapper for the RDD API if you're interested in some of the lower level APIs, but you want to access them from Python. So all of this great stuff is super cool, but I decided that since this is a Spark summit, I was going to talk about Cassandra first. And this is the explanation of what Cassandra is according to Wikipedia. It is a hybrid between a key value and column-oriented or tabular database management system with a data model that is a partitioned row store with tunable consistency. So I know that's really clear, so I thought we might want to go over what exactly that means and why that's important to know when you're connecting to it from Spark. And we're going to focus really on two things. What is a Cassandra partition? Because here at Spark Summit, we're obviously talking a lot about Spark partitions, and the two are unfortunately not the same. And then we'll also talk about how Cassandra actually puts Cassandra partitions into your Cassandra cluster. So where does the data actually live in the cluster, and how the Spark Cassandra connector uses that information to read data locally from your cluster. So to start with, just to show what a table looks like in Cassandra, here's an example schema. It looks a lot like SQL. You basically define a couple fields and their types. Underneath that, you'll see we have a primary key declaration. And this is the only part where we get into the Cassandra world. The first part of that primary key is what we call the partition key. And the second part is a clustering key. And these two fields that are in that primary key declaration basically describe how the data is going to be laid out inside of Cassandra. So basically, if I do an insert into this table, and an insert looks a lot like SQL as well, and I try to insert into vehicle ID 1 with clustering column 0, so for the timestamp 0, I'll actually end up making a header to a long partition in Cassandra, which will basically just be the value 1. It will then be followed by a group of the fields, so here X and Y, ordered by the clustering column, and I put that on top, timestamp 0. So if I keep adding more and more inserts to this partition, you'll see they'll get ordered like this, where it doesn't matter what the X and the Y value are, but the timestamp values will continue in ascending order. So basically, this means for every given partition ID in Cassandra, I end up with this long sequence of rows. So this whole thing is really what we call the Cassandra partition. And this entire long piece of data is going to exist on a single node. Now, within that, we basically can define a row as just one of these groupings. And this is basically how it gets laid out. So I have many rows that are contained within a single partition, and all the rows in that partition share the same partition key. Now, what's important to know about this is that because our data is ordered by clustering key, Cassandra is very good at saying, given a partition key, tell me all of the values that are within some range of clustering key values. Because you can see since the data is laid out, all we have to do is go to the right node that holds that partition key, then take that row out and cut it on the beginning and the end of our clustering range. So that's really the most common thing that happens in Cassandra. But obviously, that's very limited. It means that we can't really do broad things across partitions. We can't really do queries that are on X or Y, because X and Y basically would require us to look at every single cell within that partition to do any work. But for that, we have Spark. And that's one of the main reasons that we've made the connector for Spark. So the next thing I just want to quickly talk about, oh yeah, slices are very easy, is that it is a distributed database. So we talked a little bit about how a partition is laid out, but a partition is going to be only on one machine. So let's imagine we have 3 different machines. We have a San Jose machine, we have an Oakland machine, and a San Francisco machine. The mapping of our data to these machines is done based on something called a token range. So you can kind of imagine the token range as a very long circle of values, where we basically go from one value at the top to a max value right next to it, and we basically cycle around. We assign ranges of those values to each of these machines. So in this case, we would say that the San Jose machine is responsible for basically all of the values between around 900 and around 50. So any partition which has that address will end up on that machine. And then we have the same thing for our San Francisco node and our Oakland node. How do we actually know what the token of a particular row is? Well, we do that by looking at that partition key value that we talked about before. And basically what will happen if we do that same insert is that we'll get that vehicle ID, which will have a particular value. We'll take that value, and we'll hash it using a special internal function. That hashed value basically will turn into a value somewhere on this token range and tell us exactly what node it belongs in. So in this case, if we hash vehicle ID where the value is 1, and we get a value of 1,000 or so, that makes us know that this particular partition is going to be on the San Jose node. This also lets us know that when we're reading data, it's really easy to find that particular partition, because if we say, where is vehicle ID 1, we can simply hash that key again, go to that node, and pull it back off. Now, given all that information, I know that was a kind of lightning run-through of how Cassandra works. This is how the Spark Cassandra connector uses that information to pull data into Spark with data locality. So the first thing that we do in the Spark Cassandra connector is we realize that that long range basically gives us these sets of tokens that all correspond to a single machine. And we then break that up into Spark partitions. And here's where we're going to start confusing the terminology of a Cassandra partition and a Spark partition. A Spark partition is going to contain all of the Cassandra partitions for a token range between 2 values. So for example, we might break up all of those values that are owned by San Jose into 4 different partitions, where each Spark partition contains 100 Cassandra partitions. Now, in the real Cassandra world, our token range is actually 2 to the 63rd values, so it's much larger than this. But basically, this is what's going to happen under the hood. And since we know that all of those tokens should exist on that particular machine, we know that when we run a read command, we can actually pull all of those data from that machine, if we have Cassandra running, into a Spark executor on that same machine without incurring any network traffic. So we know that as long as the Spark executor on San Jose asks for data between 500 and 600, it doesn't have to ask any of the other machines. And because of that, we don't ever have to leave the node for data. We're always going to be node local when reading. Now, to actually read that data, we're going to use the Datastax Java driver. So there's actually the same Java driver connection that you might be familiar with if you've worked with Cassandra before, is being used by the Spark Cassandra connector under the hood. And basically what happens is the Spark executor will start up a connection to Cassandra, and it will end up receiving one of these Spark partitions that says what tokens it needs to pull. It's going to take that information and prepare a select statement. And the select statement in general is going to look like this. We're going to select all of our values from this table where the token is at the beginning of our range and the token is less than the end of our range. So basically, we're just going to say, give us all of those partitions that should be within this Spark partition and pull them into this executor. So you'll see that those values will just get popped in there. And then we start pulling in data. So Cassandra Java driver actually pages in data. So it's not going to pull all of this all at the same time. It's going to pull it in blocks and continuously pull those in until the entire query has been satisfied. So that lets us still kind of work in the iterator framework of Spark and not actually pull everything before it's needed. Now, when we write to Cassandra, we're basically going to use that same kind of idea, but we're going to do it in reverse. We're going to use the Datastax Java driver. We're going to group things based on partition key, and then we're going to write them back to the database. Now, For those of you who are a little more familiar with Spark or with Cassandra, you've probably heard that it's really not a good idea to batch a lot of stuff together. Well, there's a caveat to that. And the caveat is that if you are grouping everything based on your partition key, it's a very good idea. Because Cassandra internally, like we showed in the storage engine at the beginning of this talk, if everything is in the same partition key, it belongs on the same machine. It belongs on the same machine, and the Cassandra process, when it's actually writing that data to the machine, can actually group it into a single mutation, so it becomes extremely efficient. So when the Spark Cassandra connector does this, it'll basically have an executor, which will make a connection to Cassandra. And then the RDDs that are being saved to Cassandra will basically serve up blocks of data. And those blocks of data will be grouped based on the partition key of the Cassandra table that's being written to. Those blocks, or the groups, are going to start filling up with data. And once they've reached a threshold, or you have a certain number of groups, we'll take that full group and we'll write it over to Cassandra. And then that will continue until all of the blocks have been taken unwritten to Cassandra. So basically, we'll try to do this efficient grouping as we're writing to give you the best performance you can on writes. So that's the basics on how it works. And I wanted to give a more high-level view of how you would actually use the API. Because knowing how it works in the fine-grained details doesn't really help you a lot when you're trying to actually write your application. So we have two big sets of APIs. We have a set of RDD APIs. And of course, we're also data frame compatible. If you're familiar with data frames and data sources, we provide a data source for Cassandra that you are also free to use. Within the RDD APIs, that full table scan, that read command that I was talking about, is accomplished by something called SC Cassandra table. All you have to do is import our implicits from the COM Datastax Spark connector package, and you'll be able to call SC Cassandra table with a key space and table name, and that will automatically create for you an RDD that represents all of the information in that particular table from Cassandra. We also provide a full set of type conversion tools so that if you want to read all of your data from your table directly into a case class from Scala, you can do that just by specifying that as a type parameter, and you'll actually get an RDD of type my class instead of an RDD of our generic Cassandra row objects. So this is all really good, but one of the most important things to know about when you're using the Spark Cassandra connector is that reading all of the data out of Cassandra is almost always not the right thing to do. You really want to limit the amount of data that you're pulling out of the database as much as you can to answer the problem that you're currently trying to solve. And for that, we offer two different little functions here that allow you to push down CQL to Cassandra. So like I showed before, we're actually executing CQL queries under the hood on our executor. And because of that, anything that you can do in CQL can actually be done in bulk through this API. And we do that here, first using a select statement and the other using a where statement. The select statement is the same as doing a projection. It basically will tell us to add onto our query at the bottom there, instead of having a select star, we'll have a select column name. And that will mean that when Cassandra receives this query, it's not going to serialize the entire row. It's only going to serialize the fields required by this query. So in this case, only vehicle ID will be pulled out of the database. The second field, which is a where clause on that timestamp, is a slice. And if you remember I talked about before, Cassandra is very good at slicing on that clustering key value. This is basically taking that great ability to slice on clustering key values and distributing it across all of your partitions at the same time. So with this particular clause, we will not have to read all of the data in the database, pull it into Spark, and then do a filtering. We'll only pull the data out of Cassandra that is expressly required and fits this particular predicate. So that's how you're going to be able to pull in huge amounts of data, but also not pull in any more data than you actually need. If you want to do distributed key retrieval, so this is a slightly different use case. This is where you have a whole lot of different partition keys, and you want to use all of these partition keys and pull them out of Cassandra in a distributed way. We have a join with Cassandra table method, and this is basically a direct join. So you can imagine that you have an RDD that's filled with all sorts of different partition key values, and you want to pull just those rows out of Cassandra. What it will do is it will map those keys directly into the executors and pull those values from whatever node they happen to be on. And you might notice that since your RDD might not have your data sorted in the same way that Cassandra does, we won't be pulling directly from the local node. Well, we actually thought that if this is going to be a problem, we should make a way to actually reshuffle that data to align it with your Cassandra cluster before pulling. And for that, we added an API called Repartition by Cassandra Replica. That lets you basically specify a table, which will then take all of the keys in your RDD and organize them so that they will all be drawn locally from a Cassandra node that they happen to reside on. So that's why I've kind of switched back from my tie-dye to complete solid colors, because this kind of illustrates that we've taken all of that, done a bulk shuffle in Spark, so that now when we do our reads, they're all going to be local. So this combination is pretty powerful for those folks who are getting an incoming stream of data and have a whole bunch of partition keys that they want to do work on, but they don't want to do a full table scan over all of the data that's in their database. So in addition, we also provide, in case those two APIs or all of those APIs are not enough to do the specific things in Spark that you want, we provide a distributed pool for prepared statements and sessions. So if you happen to have some operation you want to do that isn't well defined by just select statements or inserts, we provide this Cassandra connector object, which is fully serializable. And when it runs on an executor, will actually create its own session pool automatically for you under the hood that you are free to use and use whatever queries you want with. In addition, this overrides the prepare method of the session, and instead of using the normal prepare, this will actually check a executor local prepared statement cache. So that means you can actually prepare things over and over using this kind of methodology, and it will actually pull out a live prepared statement if one exists on that machine. So if you have to do something more complicated with check and sets, or you happen to want to do a bunch of inserts, or you want to do a select and then an insert based on your select, this is how you can kind of use these objects and these pools to really simplify your code. So you don't have to worry about session management or your prepared statements. It'll all just be done for you. So in case all of that was, a little unfriendly, and you saw, you're really more of a fan of Spark SQL, you really want to do data frames, because data frames are a lot simpler to reason out, and they do a lot of the cool optimizations under the hood, we still have your back. We have a DataSources API, and all you have to do is specify a format, and then within the options table, you have to specify the key space in the table. So when you do this, basically, it will just return for you a data frame that represents an RDD that represents all of the data in your Cassandra table. And if you look at our example underneath there, we actually put in a little shortcut just in case you want to not have to write in maps and formats all the time. And you can use the Cassandra format function that we added implicitly to just specify table and key space. There's a bunch of other helper functions as well. I suggest you check out the data frames documentation I have linked there below if you want to also simplify the creation of maps or specifying other parameters. And the cool thing about working with data frames is that when you work with data frames and you do a select or a filter or anything like that that ends up making a query plan that has projections or that has filters, those filters and projections are going to automatically be pushed down to Cassandra if they can be. So you don't even have to worry about figuring out what predicates work and what predicates don't, or whether or not you can do certain things, because the data source will automatically do that for you. The one thing to note about this is that currently the data source only implements what's called pruned filter scan. And pruned filtered scan, as it says, really only lets you do two things. It lets you prune and it lets you filter. So if we get projections, which basically means we only want to get certain columns, we can do that. And if you want to filter, if you have a predicate that we can possibly push down, we can do that. But if there's something like a join or a repartition or something like that, that's something that isn't exposed to the data source right now. And that's something we're looking at trying to fix later, but currently can't be optimized away. So for recent features with the connector, so we do support Cassandra 3.0, which is the most recent major release, and all of its subsequent minor releases. We support materialized views and Sassel, which might be sassy, and I believe I typed it in wrong. We have some new advanced Spark Partitioner support, and we, of course, have a great performance boost on Join with Cassandra table that was recently added. And just to talk really quickly about our Spark Partitioner support, this is a rather advanced feature, but I'd really like to go over it for those folks who are aware. Whenever you do a key to RDD within Cassandra, or within Spark, you actually have a partitioner that RDD owns. Now, knowing that, we realize that there's some really obvious things here. Cassandra data is partitioned with this hashing function that we went over. Spark data can have a partitioner, which tells you which data is in which partition. We should really use the idea that Cassandra's partitioner should be in Spark. That way, when you do shuffles, when you do joins, you don't actually have to shuffle everything. So to take advantage of that, we basically took the keyby function, which is normally available on any RDD, and we made it so that if you key on the partition key of your Cassandra table, we will actually take that RDD and automatically assign it a partitioner that would emulate Cassandra doing that exact partitioning. And this means that if you take this RDD at the bottom that now has this partitioner, and you do anything that requires a co-group on this particular key, so for example, if I wanted to group on zip code, I'd be able to do that without a shuffle now, because it's already organized by key, and we were able to express that information to Spark. Or if you could imagine, if we had another table, which also had user ID as its key, we would be able to actually join those two tables together without any kind of shuffling, because we already know which values are in which partition based on this Cassandra partitioning. And this is a quick little example of that. We basically can take the partitioner from the first RDD, we apply it to the second RDD, and now we end up with two RDDs that have the exact same partitioning, and I can join them together without any shuffles. So this is a new capability. I encourage you to try it out because it actually has a lot of interesting implications and speed-ups that you can use. So basically, the kind of things you can do with this is you can start doing self-joins on your partition key. You can do all kinds of groups within Cassandra partitions. And you can do joins with other RDDs. So another really interesting thing is if you join against any other RDD, that other RDD will now partition itself using this Cassandra partitioner. So you don't have to actually shuffle both sides of the join like you would in most joins. The enhanced parallelism in the join with Cassandra table. So if you've ever used the join with Cassandra table method before and you wish that it was a lot faster, we just recently increased its speed by increasing concurrency and parallelism within the method. We've seen up to a 5x speed increase. So if you used this before and you weren't satisfied with how fast it is, you should definitely check it out now. This is thanks to Yarek, who's one of the new members of the Datastax analytics team, who added a lot of interesting asynchronous execution code into this. And as I'm wrapping up, I just want to note that the open source Spark Cassandra connector wants you. We want you to be a part of our project. We are a full open source project with a mailing list and IRC and everything. And we love to have a community involvement. If you have a bug that you find, if you have a feature that you really think we're missing out on, or if you just see the docs and you say the docs are not good for this particular session, please let us know. Please join us and help us out and figure out how to make this an even better project. Now, in case I didn't mention this, I do work for Datastax, so I'm going to also push more of our awesome Datastax Academy stuff. If you check out our blog here, academy.datastax.com, we actually have a full series of videos that describe how to use Spark, all the intricacies of Spark, and using Spark with Cassandra. And the best part, of course, is that they are all free. So you'll be free to go through this in whole course of instructor-led videos that will teach you how to work with Spark. And of course, I'd love to see everyone at Cassandra Summit, where we'll probably talk a little bit more about Spark and Cassandra, which will be September 7th through 9th this year. So thanks, everyone, for coming. And if anyone has any questions, I'd love to hear them.